What's up, everybody? In this video, we're going to talk about how to explain a substance's physical properties by comparing their intermolecular forces. Specifically, comparing how strong their intermolecular forces are, what those intermolecular forces are. We're going to do that by analyzing the melting points of two substances, H2O water and NH3, commonly called ammonia. This whole process starts by first looking at the Lewis structure in the shape of each molecule. Maybe we should back up and say too, this process, starting in this way would also only apply for molecules. Here we've got hydrogen, a nonmetal bonded to oxygen, another nonmetal. So these things are covalently bonded together, and therefore water is a molecule. Same thing with NH3. So anytime your substances are molecules, you got to start with that Lewis structure. And as you do that, you want to also make sure to consider the actual shape of that Lewis structure, right? So water has this bent arrangement, and if you did the Lewis structure of NH3, it kind of has this little pyramidal shape. And you'll see why that shape is important in a little bit, so just put a pin in that for now. The next step is to check the electronegativity differences between your atoms, right? You basically want to see, okay, we've got these bonds in these molecules. Are those bonds polar, and how polar are they? You could look up these numbers if you want to. I believe oxygen is like a 3.5, and I'm just going from memory on that, so I might be a little bit off. Hydrogen is a 2.1, so the difference in those electronegativity values for water is about a 1.4. And then if you did the same thing in NH3, nitrogen is about a 3.0, hydrogen 2.1, so the difference here is a 0.9. All right, the next step in this beginning stage is to compare the polarities of these molecules. Are they even polar at all, right? Not all molecules are. And that's why we needed the shapes of these molecules, because now I can look back at H2O. I can see from the electronegativity differences that these bonds are polar, and from the shape of the molecule, I can also see that there's asymmetry here, right? These polar bonds are asymmetrically arranged, and anytime a molecule has those two things, polar bonds, with an asymmetrical arrangement, you're talking about a polar molecule. So I'm just going to label water as polar for now. Same thing in ammonia, by the way. Their bonds are polar and they're asymmetrically arranged. So we can label both of these as polar molecules. That's not all we want to do here, though, because we also want to compare the polarities. When it comes to intermolecular forces, you often want to know which of the molecules is more polar, and that's where that actual electronegativity difference comes into play. Because the difference in water was 1.4, I can say that water is not just polar, it's more polar, and ammonia is less. Another way you might say that is by describing water as having a greater net dipole. Okay, the next question we want to answer is, are there dipole-dipole forces between these molecules? In this example, both water and ammonia, NH3, are polar, and anytime you get polar molecules near one another, they are going to be attracted to each other with dipole-dipole forces. So I'll just label beneath each of these that yes, indeed, both water and ammonia will have dipole-dipoles. And there's an important follow-up to this too, because some dipole-dipole forces are extra special types, extra strong dipole-dipoles called hydrogen bonds. And to get hydrogen bonds within the molecules, maybe we should back up and do a quick little recap of what it takes for these dipole-dipoles to be considered hydrogen bonds. So here's what you got to have. You have to have one of the molecules with an element, and I'll label it X, because that X could be any one of three: oxygen, nitrogen, or fluorine. And that's we'll just call it like molecule A over here. And then there's got to be a second molecule, we'll call it molecule B, and that's also got to have an X. And that X again is either O, N, or F, but this time that X has a hydrogen coming off of it. And if your two molecules meet that qualification, then the attractive force between them, the dipole-dipole force between them, is going to be considered a hydrogen bond. In the case of water and NH3, if you got two water molecules near each other, they will of course meet those qualifications. So the dipole-dipole forces in water are hydrogen bonds. The dipole-dipole forces in ammonia would also be considered hydrogen bonds. And at this point you might be saying, I don't really even see what's going to be different between these two molecules, right? They both are polar, both have dipole-dipole forces, and both have dipole-dipole forces that are considered hydrogen bonds. What is even different about them? Well, even though they both have hydrogen bonds, you can still compare the strengths of those hydrogen bonds, the strengths of those dipole-dipole forces. And for this, we're going to look back one last time at those electronegativity differences, which told us that water is not just polar, water is more polar. Because water has a greater net dipole, its hydrogen bonds are going to be stronger. So I'll just label that here in purple. And because ammonia was less polar, its hydrogen bonds, its dipole-dipole forces are going to be weaker. And all of this work was to say that one thing. That's what we needed to know, is that water has the stronger intermolecular forces, ammonia has the weaker. Because as soon as you know that, you can now compare the property that you're trying to compare. I'm going to list these out here in this bottom left-hand corner of the video screen, but just making a quick list of what types of properties are the result of substances that have strong attractive forces. One thing that you're going to notice is that strong attractive force substances tend to be solids or liquids at room temperature. That's not what we're trying to answer here, but it's something that often comes up. Another thing that these substances tend to have is elevated things like boiling point. I'll just write BP for now. Elevated melting points, elevated enthalpies of vaporization is another common one, because all of these processes, boiling, melting, and vaporizing, all require those intermolecular forces to be broken. And if those forces are stronger, like they are in water, it's going to take more energy to break them. So you're going to get elevated levels for these things. There's one more common one that I'll list out here that comes up as well. It's called vapor pressure. This one's unique in that the vapor pressure is usually lower for substances with strong intermolecular forces. The point of this, though, is to compare these guys in terms of melting point, which of course I can now do. Water has stronger hydrogen bonds than ammonia, so therefore water's melting point is going to be higher, at least that's my prediction. Ammonia's melting point, therefore, is going to be lower, and I can go back and answer the original question, which substance will have the lower melting point? I would say NH3. That also wraps it up for this video. Thanks a lot for watching.